speaker is Makoto Nagata, and he got his PhD and Master in Physics from Yakushima, I can't pronounce it right, in Japan, 1991-93. Then PhD from Hiroshima University, Japan also, 2001. Now he's an associate professor. Then he joined Kuba University in Japan as an associate professor in 2002. Now he's a full professor in the same university. Research interests include flight techniques targeting high-performance mixed analog, RF and digital bin size systems, with particular emphasis on power, signal, substrate, integrity, and electromagnetic compatibility, testing and diagnosis for 5D and 3D system integration, as well as application for hardware security and hardware safety and cryptogenic electronics for quantum computing. The senior member of IEEE of Japan. He was an associate editor of ITV Transactions on Bin Size System from 2016 to 2020.
Thank you very much.
Thank you very much. Hello. Hi. Hi. I'm happy to see many of you are still be interested in those kind of talks. I think some of the topics would be quite unusual for you, probably. This is also kind of that. I will be talking about the hardware security and the safety. This is a bit wide scope, I would say, so that if you have seen any difficulties or not too easy to understand this, I can explain it all. So, but before going to the major topic, I just would like to introduce my university to you. I'm working in the Kobe University in Japan. This is the, I don't know how many of you are knowing the place that Kobe is. Kobe is, simply speaking, Kobe is next to Kyoto, Osaka. Osaka, Kyoto is well known, right? But Kobe is kind of the sister cities to them. And the Tokyo, as Ikeda-san is in the University of Tokyo, it's a capital city, right? There. The Kyoto is like 500 kilometers away from Tokyo, but we have a very rapid Shinkansen, you know, that it's a quite high-speed train. Shinkansen, yeah, just 3 hours. You can get to the Kyoto, Osaka, Kobe area from Tokyo, so it's super easy. If you come to Tokyo, you need to come to Kobe as well, right? This is the one thing you need to remember today. Okay, so my team, I have several students. It's not so big, but we have the senior guys as well. And here, this is myself, and also I have here another professor called Miki-san. He is kind of a super expert in electrical design, especially for the cryogenic. It means that you have extremely low temperature, like 100 degree Kelvin or even below, for the quantum computers, controlling analog circuitry for their use on the quantum fields, right? In the extremely low temperatures. But I will not go into the details because this is a topic by the Miki-san, right? It's another professor in my team. But I'm working on the security and the safety, and it's combination of security, safety, and quantum. We are called our team as the secret. This is the name of our team, right? So, okay, if you have some interest, please visit our website. Now, okay, this is the topic, outline of the topic today. After some introductions, I will talk to you about the electromagnetic compatibility problems in the IC chip device. What's the meaning of the electromagnetic compatibility? I will let you know right now. And also the hardware security problems, HWS. And this has a very much the relevance to your knowledge in the field of electromagnetic compatibility. So why this kind of things that you will run? This is a quite tutorial type of your talk, I would say. So you may learn something from my talk. And there are, of course, there are some the integrated circuit chip solutions for the hardware security and also the hardware electromagnetic compatibility. I think you should see the screen on the right-hand side. That works well. Left-hand side, sometimes it's unstable. Okay, so here you see, this is the kind of the relationship between the IC chip designs and electromagnetic compatibility for the safety, and the hardware security for the security and the privacy. If you're designing a chip, you would be focusing much on the performance of your circuits. This is the natural consequence of your job. But as engineer or as expert, you need to be concerned about some other aspects of the electric systems. One is the safety and the reliability. Another one is the security and the privacy. Those two things always need to be considered by you. Otherwise, who can manage things? Who can guarantee that your system is okay for the safety and also for the security? No one could this. You are designing a chip. It's kind of the heart of the developing the electronic system. You're key persons. You need to be more knowledgeable, not just for the electricity, but also for the other things like safety and security I'm talking about, right? And so this is a kind of the image what we are considering if we are talking about electromagnetic compatibility. This is the topics of IC chips, but you see here is a car, obviously different from the chips. But all the chips you're designing will be situated within a car. Not just for the fully electric vehicle, but even for the like hybrid cars or anyway, the kind of the smart cars. Always your chips will be within that car. So of course, microprocessors, AI accelerators, memory, sensors, actuators, everything will be controlled by the IC chips, right? But you have a car here. This is a very strange room. It's called anechoic chamber room. This is a kind of a special room for the measuring the response of the cars against the incoming electromagnetic powers. Or sometimes we also measure the electromagnetic powers coming even from the cars. Why this happens? Because every time car starts to operate, some of the electricity starts to work, right? And sometimes the very high switching happening on your IC chips, even in the car, that will emit some electromagnetic noises coming from the cars. And what's the meaning of the electromagnetic compatibility? This is the way we need to consider the two sides. One is the control of unwanted radiated and conductive emissions. As I mentioned, if circuit starts to operate, some of the electromagnetic noise will be radiated from your device. This is the emission part. At the same time, you see here is some strange antenna facing to the car. Sometimes a big EM, from now on, I will call EM for the electromagnetics, right? It's an abbreviation of electromagnetics. I will say just EM. So if you have the big EM power coming directly from antenna onto some of the parts of the chassis or directly to the electronic component of the cars, something will happen. For instance, unexpectedly, like a light starts to on, or even the doors becomes open, right? That kind of things could happen because of the invisible interaction of the EM powers with electronic components within your car. This is the immunity types of the things. Immunity to radiated and conductive disturbances. It's called electromagnetic susceptibility. So immunity and the susceptibilities always need to be considered in parallel, concurrently. This is the meaning of the EM compatibility. You just not focusing on the emission. You need to also consider the injections, immunities. You will emit your noise from your designed chips. At the same time, you will be attacked by the noise coming from outside. Both ways, always you need to consider. This is the idea of your safety thing, right? And, this is another thing that's quite important. This is set up by the kind of ECR10, it's called the ECR10, set up at the UNECE. It's a kind of the law. Every cars exported to the Europe needs to be compliant to the ECR10 set by the European Community. So this is the kind of the standardized their performance, you need to be satisfied. You need to make your design satisfied with this ECR10 rule. It's always be updated, so all the time you need to be kind of be knowledgeable about this. Right? What kind of noise we are talking about here? Here is a car, electric vehicle, in the charging state. Some of the big charging system will be powering the batteries within a car. If we have the home antenna, it is the kind of the wide frequency, wide bandwidth antenna located just in front of their charging system. And then we see the chart like this. After the measurements, we can get the chart like this. Horizontal axis gives you the frequency from almost like a DC level to the 6 gigahertz. Vertical axis gives you the kind of the noise level. Why? Can you imagine that you just measure the noise coming from their charging stations? We have a big noise here, like a peak in the 800 megahertz range. Well, another peak we would see 2.5 gigahertz to the 6 gigahertz, right? Those are very strange shapes, but they are showing you there exists some noises. If you're knowing about what frequencies you are using for your cellular phone, like 800 gigahertz, you are using 2.1 gigahertz, you are using 2.5 gigahertz up to the 3 gigahertz you are using. All depends on the country you are living, but normally that you are using this range of the frequencies. It's so sometimes we call this kind of a sub-6 gigahertz. It's named sub-6 gigahertz. It's a meaning or the frequency range of interest that people are using in the cellular phone systems, right? So that we always need to consider what kind of noise you could measure in the sub-6 frequency ranges. This is a different measurement setup for the capturing the incoming noises from the power module using the high efficient gallium nitride devices for the 12 watts. Not so big power. But if you have the measurements like this, again you see the very strangely similar shape you could see. Like 800 megahertz, you see some big noises here, and you have some other spectrums. Very, very strange spectrums, but you see the noises in the frequency range of the up to 6 gigahertz, as I mentioned. It's called the sub-6 gigahertz range. You see many noise components. And now we have the 3 different colors. One is blue, another is red, and also the other one is black. Black is kind of backside, floor noise. Once you start to operate the gallium nitride modules at the frequency, switching frequency of like 100 kilohertz, the red cards you see. 100 kilohertz switching frequencies, but you see the noise of the frequency components of the 2.5 gigahertz points here. Obviously, quite important types of the noise are coming here, because this will affect your cellular phone running at the 2.1 gigahertz, right? Then once, if you increase the switching frequencies for the higher level of the efficiency of the DC-DC conversion, you see the higher level of the noise frequency. So this is a natural trade-off between your efficiency and the potential disturbances coming from your device. Now, now that I think you're understanding all that, I don't do just seeking for the high efficiency, but also at the same time we need to suppress the noise. Otherwise, some other system will be destroyed because of your switching devices. This is a natural measurement result. So what's the problem here? This is the actual kind of industrial drones. Sometimes we name this as unmanned aerial vehicle. I think now the people are often using some kind of the drones in the situations. But drone, by definition, everything needs to be well wirelessly connected. Otherwise, no one can control. If you see the drone, you need to identify who is operating that drone, where that drone is coming from and going to. Kind of that. It's autonomous control of the drone system. It's coming up, right? That for instance, in Japan, we have good cellular networks. Cellular networks means that if you're being your phone, you can be connected everywhere, right? Similarly, the drone can connect the cellular channels or the control all over their nations, kind of that. Those are quite important things, right? That you need to control the drones. But what happens if they have a big noise sources within the drone? Drone is relying much on the wireless communications and also the global satellite-based the positioning system, GPS kind of that. That is also be needed. Everything is wireless connections. But if you have the noise sources within your drone, that may deteriorates the performance of the wireless communication, performance of the drone itself. It's not good, right? This is another way of you need to consider how that the safety could be guaranteed, assured by your design. Like here, that the usage models of the drone, industrial drones here. The drone can see the status of the railroads, or the drones can be continuously make a kind of a surveillance on the big towers within the mountains for the electrical connections and power grids on the through the air mountains. And also sometimes drone is usable for the delivering the things, automatic delivery. If you are living not in the city side, someone needs to deliver the things, tracks. Of course that could happen, but drones could be more easy, right? That they can fly to some not urban, in the rural areas, and that can be autonomously bring your things goods to like houses in front of your houses, kind of that autonomous the delivery that could happen. But every such the industrial aspects of the usage models of the drones, we need to consider how that EMC is managed well, and also how that the security is managed well. Otherwise, well, I can't believe that if the drone is coming, someone is just put on in your house, in front of your house. Is that yours or the someone else? Or is it safe things, or it's bad things inside? Kind of that. Always people need to be satisfied. But once that the system starts quite well, I think that people can be systems can believe, makes the people believe about the operation of the drones. Now, this is the actual measurements we have done on the initial state of the industrial drone. Of course, nowadays everything gets quite well, but in the beginning, we just make a measurements about the industrial drone. This drone, it's size-wise like this, very big ones, with this industrial drones, right? And try to make sure that the drones are okay with the EM viewpoints. But once we make the measurements, once again, we saw very strange frequency components just coming from the drone. You see here is our noise components for the 800 megahertz range, as I mentioned, but it's a cellular. 800 megahertz is quite important for the drones because that's the frequency that the EM waves can go through the air mountains. Low frequencies sometimes quite important for the distant the control of the drones. So that we need to reduce the noise in the frequency range below 1 gigahertz. Here is a huge noise we see, and also the satellite positioning this frequency range. We need to suppress those noises. And again, other channels for the cellular, Wi-Fi, and also for the cellulars in the coming six generations will use those kind of frequencies. So all those components we recognize just by measuring the noise coming, EM waves coming from the industrial drone, 2 centimeters away from the airplane. This is another key point I need to say. Normally, the EM professional make the measurements for their target 6 meters away from the target, 6 meters. But here we put the antenna 20 centimeters. This is the different from their conventional measurement requirements on the electromagnetic compatibility. But now you are designing a chip. Your device will be within the drone. Your wireless connection device will also be within the drone. We don't think about the 6 meters. We just need to consider well below the 100 centimeters kind of stuff. So approximate interference between the noise generators and the noise absorbers are quite important. This is another message. This is a very, very message for the people like you designing electromagnetic chips, IC chips, integrated circuit chips, because the chips are always be quite tiny, and the chips are nowadays very, very closely located, especially for the chiplet designs nowadays. Your digital chip and your analog chip will be situated within the 1 centimeter, meaning that you need to be nervous about the noise coupling problem. That becomes much, much more serious than ever, I would say. So here is the kind of the standardization in the supply chain up to the car manufacturer. This could be the final product vendor. Well, as I mentioned, the car manufacturer needs to make their products like a car compliant to the ECE R10 set by the European law. But this car manufacturer will request the electric module suppliers like our autonomous driving systems or like a sensory systems or sometimes talking about the media control. Those are all the sub-modules set to their cars are requested to be compliant to the another type of the certification like a CSPR. It's called, sometimes we pronounce this as a Cisco 25. This is another regulation for the communication interference. And also ISO 11452 and some others. And then electronic module suppliers will request the IC chip vendors for their IC chip products to be ready for the measurements about their EM and EM emissions. Those are set by their IEC types of the standardizations. So you are focusing on the transistors, or you may focusing on the register transfer level, right? That after your synthesis, you may set up the chips, that will be okay for the sign out, or everything's okay. But this is okay only for the manufacturability of the semiconductors, not for them, right? It needs to be considered from the design stage. It's a very, very recent or catchy terminology is pre-silicon. It's quite needed. Pre-silicon means that you need to predict, you need to make some good simulations before going to the tape-out. Once you make a tape-out, once you got the chip, once you measure the chip, your functionality is okay, performance is okay, but what about noise? If noise is not okay, that will not be ready for the market. That this is a very important and difficult thing you need to learn. Sometimes you need to have your idea of the multiphysics situations. Even you are designing RTL level, but you need to consider how that EM field will be simulated by the field solver. And you need to make your visions wider, much, much wider than before, to become your experts, talented designers. I'm expecting you to be such kind of people, right? Okay, so the IC chip test standards, I don't go into the details. There are many, many updates. It used to be their EM emission was measured up to 1 GHz, but as I mentioned, we are always talking about the sub-6, meaning that you need to make measurements up to the 7 GHz at least, right? And also for the millimeter waves or the like FR4, new radio, FR3, 4 types of the things for the coming 6G, you need to consider the measurements up to the 30 GHz, so even higher. So their noise needs to be considered with the very, very broad frequency range, right, nowadays. And well, this is another very tutorial types of things. If you consider the chips, what's the size of the chip you're talking about? Probably like a 2 millimeters times 2 millimeters, quite tiny, right? But the noise measurements I mentioned is 10 centimeter away from the chip, or even in the room, 6 meters away from this device. EM noise can be captured because it's a kind of a distant traveling. If you put the antenna far away from me, like the other corner of this room, that antenna can catch the noise if I have some IC chips, kind of, right? Your chip is quite too tiny, but everything is densely compacted within the die. All the power consumption would happen within the die. Power currents are consumed within the die. But those high power current will create the high power EM noise radiated from the chip, right? So you need to consider, right? The chip is quite tiny, but the board is like a 10 centimeter, and the far field EM emanation, its emission would happen more than 1 meter. So different size scales you need to consider, right? Here is an example measurements. Here we just put the chip here, and this is a magnetic probe. It's a kind of the one-channel coil. Very simple measurement techniques, but quite powerful. If you put the one-channel coil here just on the backside of the silicon chip, you can measure noise up to the 0.5 gigahertz, as I mentioned. In this case, the chip was operated at the clock frequency of 106 megahertz. But if you consider 20th harmonics of the clock frequency, that will coincide with the 2.1 gigahertz band for the cellular. Here's a 2.1 gigahertz. Obviously, this is a very high noise. Why this happens? Because of the regular switching of your device. You are designing the digital circuits. Always, everything needs to be well synchronized to the clock frequencies. This will give you the very pure alignment of your noise components happening in the clock period. For instance, 106 megahertz means that it's almost like a 10 nanoseconds, right? Every 10 nanoseconds, you have a big power consumption happening. This is very, very regularly happen. That will create the high bandwidth harmonics noises coming from your device. This is really natural consequence of your design, right? Because that you need to align all the switching happening at the edge of the clockers. And that more higher performance, people will push more to their clock edges for the high frequency operations, of course. This will give you a high performance, but that's the same thing. You see high level of the noise coming from your device. So this is another thing, another way that you need to consider. Oh, it's my design is okay for the high frequency operations, but is it okay for the EMs? Particularly if you're designing a chips for your automotive areas, right? And this is the kind of the measurements, how that noise is so impactful on the performance of the RX channel, receiving channel. The wireless communications, the weakest path often happens in the receiving side, because reduced power will be caught by the front end, and that will be the amplified for the further processing, right? The sensitivity, highest sensitivity happens in the receiving side. So here is a kind of the noise power density measured just by the one-channel coil on top of the device. By the way, if you put another coil on even on the printed circuit board, the results are not so different. So you can make measurement not just on the backside of the silicon, but also everywhere on the die, on the board. Sorry. So if you make a measurements like a power, it's magnified in the 2 kilohertz the resolution bandwidth, meaning that this power is measured for the 2 kilohertz bandwidth at the frequency of the, for instance, 2.1 gigahertz, 2 kilohertz bandwidth. But in reality, for instance, in the wireless communications, people are using wider frequency bandwidth for your given channel, like 1 megahertz, 1 megahertz. If you integrate all the noise over the total bandwidth of 1 megahertz, that will give you a number for the channel power. This channel power is measured just for the noise in this case. But you need to convert the channel power coming from their base stations away from you. Like 1 kilometer away from you, there must be some, you see very cellular antennas everywhere in the Cairo city. I saw the big ones in the top hills. But those were coming to your cellular phones, and that's the channel power should be much, much smaller, actually, than those noise powers. So this is a quite comparable number. And the numbers just measures 5 millimeters away from the die, very, very close to the die. That's the field strength of 10 to the 100 microvolt per meters. The number itself is not the matter, but it's quite comparable to your UE stands for your user equipment, meaning that your receiver. This is quite a similar number for your receiver receiving the power coming from the base stations here. So now noise is you can't ignore. It's almost comparable, meaning that you need to reduce the noise, otherwise that your cellular phone wouldn't work. But of course, this is a matter of the distance. So now the systems are designing in the size-wise almost like a 10 centimeter or 100 centimeters. That is okay. But if you put your logic devices with your wireless devices very, very close to each other, like within 5 millimeters, you need to consider this kind of things. Like chip stacking technologies or 2.5 technologies situating 2 different dies within a single package. In that case, you need to consider, right? Okay, so noise is quite impactful. And of course, those kind of things can be well simulated beforehand. This is the kind of a system level simulator. Wireless RS channel can be simulated with the existence of the interference. This is so-called electronic system level simulation. Here we have the kind of the macro model of the RF front ends to the baseband digital conversions. And here is RF, the RF circuitry. There's a filter and a program gain amplifier and the last stage filters. The results will be coming to the AD converters for the digital backends. So this port is the receiving front end and quite vulnerable to the incoming noise. Those can be captured in the system level simulation, and how these systems can be tolerate against the incoming noise. Here is the noise data incoming, and that will be attached to the incoming signal to the antenna, and that will be given to the front-end circuitry. So horizontal axis gives you the signal level, the incoming signal level, and the vertical axis gives you the system level throughput. By the definition of the 3GPP, this is a kind of water consortium talking about the wireless communication performance. And this is defined where the minimum power you can receive correctly for the throughput of the higher than 95%. This is the kind of the performance medley. If you have a receiver chain having the throughput of the 95% for the incoming signal well below the minus 100 dBm per channel. This is the perfect number. Minus 100 dB is a kind of key parameter, right? Normally, without any noise, that your front end works quite well. Designed well, implemented well, fabricated well, and actually they're working quite well. 100 dBm per channel, 5 megahertz channel, that could be sensed by your front end. But once if you have some disturbance noises, environmental noise, the performance gets worse, and you request more than 90, or like in this case, more than 87 minimum power you need to have your throughput of the higher than 95%. This is the kind of the 20 dB, meaning their 100 times high power you need if you see the noise very closely to your device. So this is another, I'm trying to change the terminology, right? I just started from just the size of the noise. But now I'm talking about what's the cellular performance you can expect even under the noise, right? This is the kind of a translation of the numbers from their physical low numbers to their system level metrics. This is another way you need to consider because, oh, here's noise. It's bad. It's quite simply we can say. But what noise that system can be tolerate? This is system level people who talk to you. You need to translate your number to the system level metrics. Otherwise, you can't talk to them, right? Sometimes the people in the system level will simply say, oh, you please reduce the noise. But what's the level you need to reduce? We can't completely eliminate the noise. Noise always exists. You can't eliminate, right? So there are 20 dB reduction you need, or 30 dB reduction you need. But you need to make the reduction of the noise. It's a kind of a traded off with some other things like the cost of the design, kind of thing. But the system guys simply push you to reduce the noise, but you need to make some countermeasures to them, right? Oh, I will reduce the 20 dB noise reduction because of this simulation result showed you if you have the noise, obviously that your minimum sensitivity will be degraded for the 20 dB, so this is the reason why I need to reduce the noise of the 20 dB. It's a quite smart way to explain, right? But additionally, you would say, but for this, we need the cost of your 50% higher. Can you accommodate this? This is the counter equation to the system class, kind of that. Otherwise, noise simply exists. Noise could be measured, but simply the noise is a problematic, no solution. So you need to make some way to negotiate. Well, in that sense, you need to have your way, the sense of your interpretation of the noise level from the systematic viewpoints, right? So this is your EM problem, safety side. Now, the main topic today is security, as Ikeda-san mentioned, right? How that this topic could be connected with security? This is the question. Here. Okay, now I'm slightly changing topics, but please remember that this is a kind of the relevance to the EM topics as I mentioned. Here is a chip design. Here's a cryptographic processor like our PPC, for instance. And the data interface will give you the cryptographic processor for the specific data. That should be quite important. Otherwise, everything will be encrypted. No, that wouldn't happen. Only the important message should be encrypted. It's a kind of a secure zoning mechanism. Sometimes we call this a secure zones. Some of the data will be selectively given to the cryptographic processor. And this processor needs to be operated in a very stable environment. This is not a digital, this is a digital design, but chip itself is not just for the digital, but for kind of the mixed signal. So that you need to have your power management control to give you the very stable supply. And also your PLL, on-chip PLL give you the clocking signals. Otherwise, the adversarial people can inject some voltage glitches to the cryptographic processor on the supply side, and also their clock glitches coming to their cryptographic processor for creating some unstable operations in the cryptographic part. That could be the ward or the countermeasured by the other circuit, like the power management control unit and also PLL. Those are designs, but here, one big problem I could see from this chart. Yes, that you can do the good design methodologies for the protecting the cryptographic processor from potential attacks, but this is just horizontal. As I mentioned, EM is radiation or injection of the electromagnetic waves. Where EM waves go? Vertically. Your design is okay in a horizontal. Vertically, you don't do this. So it's quite vulnerable in this case. Someone can inject their EM powers onto the cryptographic processes. This is away from PLC, or away from PLL. And of course, that this cryptographic process is working, as I mentioned, this is also also they are clocked in the regular way, meaning that they will emit the noise. So such the high harmonics wouldn't be ignored. You need to consider high order noises coming from the cryptography processes. So here is a kind of what we can see the relevance, the relationships between the EM people and hardware security people. Here, as I mentioned, the electromagnetic emission is quite important. Just you can make the measurements of the size of the noise, and that can be interpreted by the wireless system performance as I mentioned. But at the same time, what kind of the contents you could extract from the noise? This is the additional things you need to consider. This is away from EM types of the things. EM, it's a kind of the magnitude level. You need to see what's the noise will be coming, what's the level, how often that happens, kind of just. But for the hardware security, what's the contents inside the noise? Contents inside the noise. Now we are thinking that the noise as a signal. It's a bit complicated, but if you make some analysis on the noise, you can extract some the internal operation of the circuitry within your chips. This is the interpretation, not just your system performance level, but for the contents level. What kind of the secret information inside the noise? This is the EMI analysis and the side channel analysis relevance. And also the electromagnetic immunity. This is the level of the system that can be tolerated for the incoming noise, for the correct operations. But if some of the incorrect operation happens in the cryptographic process, you get the wrong results, wrong ciphers. If you put the correct key, if you put the plain text to be encrypted, but results would be wrong because of the injected noise. This wrongness is a way for an attacker to reduce the search space of the keys, secret keys. This is called intentional fault injections. Once again, this is a connection to the EM world, EMC world, electromagnetic compatibility. As I mentioned, you need to consider how that your system, your IC chip is tolerated against the incoming noise. For the security viewpoints, what's the injecting noise will create the wrong answer from your cryptographic device. That is the source of the leakage of the secret key. Now, it's additionally that you need to consider what's the contents you will manipulate in your system from EM viewpoints. So now I think it's easily you can connect between EM and hardware security, right? So this is the kind of the measurement techniques nowadays. Another thing I would like to deliver here is that now you know that there are people are talking about the chiplets. Chiplets means that you would have the different functions, different chips having specific functions like processors, memories, analogs. Those chips will be situated on the single interposer, right? But what's their integration techniques normally that people are using is so-called flip chips. Flip chips means that your circuit will be face down for the high density connections or low profile or small footprint. Every aspect that people are talking about your flip chips. But for the security viewpoints, if you have the chip flipped down, your backside is now open for anyone, right? Because there are no circuits, no care. But you have the silicon substrate on the backside. If you have your simply you have the probing needles, you can make some measurements over the voltage variations happening on the silicon substrate. Or simply you can put your one-channel coil, as I mentioned. That will capture the EM waves. EM waves, for the EM waves, normally silicon is transparent. So the front side, from front side, the EM waves will be easily coming up and captured by the coil. And this is such idea. And also the photosensor can also be situated on the backside. You know that high frequency switching means that the device will be in a very high electric field internally. That will create the kind of the all electron pairs it's a creation of the whole electron pairs because of their high frequency, the channels. The electrons are run through their channels in a very, very high voltage environment. And then the emission will happen. That will be captured by the IL spectroscope. Those kind of measurements, all the way that an attacker can now hold the and also the active fault injections. It's a reverse side, right? This is the passive side channels. This is the active fault injections. Needles, you can create the DC biasing or high voltage passing from the backside. And also, once again, that the magnetic flux can be injected because of the EM, where it will be easily going to the front side of the chip. And the laser as well, that you can input the IR laser powering, IR laser, the kind of a shock you can introduce onto your front side. Well, the wavelengths of the smaller than 1,000 can be kind of almost like 1,000 nanometers. This is the numbers to be used for the IO injection on your silicon device. And the backside is quite open so that the attacker can do the scanning. And if the very sweet spots that an attacker can find, what happens here? This is the kind of the AES. This is the kind of the cryptographic engines. Here is the blue is the injected fault. Here is like a matrix of their all-time fault. And you see A, B, C, D, 4 different matrix, but we see the blue points having the wrong numbers without any overlap between the columns. This is a sweet spot. Once this happens, you can extract the key just by the several, like 8 or 12 or 16, their different ciphering. This is a quite powerful method for the an attacker to collect the key bytes. Okay, so probably 15 minutes. Something like that. Okay. So I think I delivered the most important message of it. So from now on, I will talk to you the more specific technologies. So you may know we have the 2 different types of cryptographic engines. One is secret key, and another one is public key. Secret key, you need to share a symmetric key between myself and you, right? The public key means that I can give you my public key, but I can keep my secret key. No one could reach this. But once I make encryption by using my secret key, you can decrypt with my public key. Meaning that this public key and the secret key are well combined, and no one can solve. Meaning that you can decrypt my message, encrypted it by my secret key, means that you can trust that the results, the text are coming from my side. Kind of that. Those kind of things can be in the other side. And finally, that we can use the key exchange without use of the key secret key. And those that AES architecture viewpoint, here is a shot. And what's the EM we need to consider here is that the contents dependency of the size of the EM. Here, you can collect all the wave shapes during the operation of the AES engines. And if you have some analysis here for the pre-sequence designs, horizontal axis could be the kind of the Hamming distance, how many bits you have the changes in your flip-flop of the secret path of the AES. We see some clear trends for the larger Hamming distance, larger size of the noise, for instance. This is the source of the side channel leakage. You can't eliminate totally about this kind of trends. You can reduce the slope, but not completely eliminate. This is the point. So sometimes people are measuring the noise more than billions of the wave shapes to extract it, to see this kind of things. And also the public key crypto is the kind of signature base. one is the 0 case, one is a 1 case. We see the difference in the frequency components here on the spectrum chart. 1 is operating and 0 is operating difference. Those kind of things are another way to discriminate the two different states in your cryptographic. This is signature based. How we can assess, this is the kind of the correlation-based analysis or signature-based analysis, but using some sort of the statistical of the analysis. How that your data collected from your measurements can not be analyzed. If you can make the two distinct groups, meaning that there must be some leakage, but you can't see any distinct difference among the measurement results. It's well hidden within the statistical analysis, right? This is the size-wise and also the frequency components-wise you need to consider. And those can be now simulated in the system-level power model analysis, having the chip model, package model, and the PCB models. And the chip model now can be given by using the standard cell library from the fabrication service vendors like TSMC. Here is a very simple chart. Here is a correct model for each of the standard cells in the library, like inverter, LANs, and flip-flops. They are all depending on their incoming patterns and also outgoing the load that each of the gates will be driving. Those numbers are all be included in the circuit level model like this. And once that current shape is pre-characterized beforehand, and the storage in your library, it's called a power library. Now you can use this model for your entire cryptographic engines, even with millions of the gates. That can be handled, right? So simulation results showed you, once again, we see some clear voltage, distributions against the Hamming distance, for instance, meaning that this design is not so good, right? This is a pre-sequence, meaning that you need to change something in your design or your data bus designs. And actually that can be well be correlated with the measurement results. Horizontal axis value, the number of traces you need to correct all the key bytes. The vertical axis will be the kinds of the rank. If you have here all the number one ranked key bytes, meaning that you can derive the secret keys just from the measurement of your waves, right? This is the simulation results, but quite much the measurement results. So the simulation now is quite trustful for the pre-sequence designs, right? Now, many chip-level mitigation techniques we have so far. I don't go into details, but the simulation is one of the key points, as I mentioned. Once you have the simulation techniques, as I mentioned, this is the kind of the chart, your front-end design, where leakage could happen in your design. This is the power of the simulation. The simulation guides you. Here is the highest leakage happening in the center area of AES. You need to make some changes in a trace and route, or sometimes you add some additional, like equalizer, kind of that. That will change this mapping of the leakage. And this is the two different designs. One is very bad design. The second one is so-so design, not perfect. But we see the simulation and measurements match well for the different designs. So once again, this is the way we can trust the simulations, by using the power model, as mentioned. And of course, those can be connected to how does the EM prediction will happen from your simulated currents. Because if you have a current numbers, you have your metal lines. This is the kind of the antenna, local antenna. The antennas are distributed all over the chip because the current are flowing everywhere in the die. You have the antennas. So, but if you have a coil 10 centimeters away from the chip, its coil integrates all the contributions from each of the wiring segments. That can also be simulated, handled by the high capacity simulators.
Now, where does the EM capturing happens for the direction of the X, Y, and Z kind of that. So simulation techniques is quite nice, but something that we still be missing, right? That you can simulate, but what else? How you can do something, right? Here is some answers. I don't go into the details, but nowadays there are many interesting technologies. Like, for instance, you may put the magnetic composite sheet in a package. Magnetic composite sheet can absorb the EM waves. It's a kind of use of the exotic material within your device, right? This is a packaging technology, so this is decoupled from your CMOS, like CMOS FinFET or even a gate all around. That would be decoupled, right? That if you have the good sense of the magnetic composite materials, you may use that one for reducing the noise. And also there are some other designs. This is also another demonstration from my team. We used the fan-out techniques. Here are the two chips situated on your very thin, like a micron level membranes. And these membranes connecting all the chips with interconnects, very fine pitch interconnects on the front side. And the back side, we can introduce the big capacitors. Here's a capacitor, directly connected to the chip, just within a few micron distance because of the thin membrane. You know, putting the capacitors just beside your device. This is one of the best way to reduce the noise, right? And also chip stacking. If you have a chip that can be stacked on top of each other, that will make another way of having the, inside you or at the position capacitors distributed within the whole stacks. That will also reduce the noise. Those are kind of the noise suppressors. And finally, the mitigation would happen. The original noise, as I mentioned, for the drones, that would be much reduced once we have such techniques in the green bands. But still we see some more noises, even under the 1 GHz or even below. So still we are looking for some other techniques, for the new techniques for the suppressing noise. And of course, if we reduce the noise, side channel leakage will also be reduced for some levels. But the correlation is so powerful so that we need to have some extra. Okay, summary. I think now that we have a common sense about you need to know about not just the IC chip design, but also for the EMC and hardware security. It's a kind of good to know if you are designing ICT system development. And also the EMC hardware problems are quite relevant. And co-design, co-development, package electric system level assembly, meaning that we need to pursue more new technologies to be included within your field. Thank you very much for your listening.
Sorry, I'm spending so time.
I have one question.
Yes, please.
So, as you said in chiplets, due to switching out things, you get like EM leakage.
Yeah.
Now with advanced technologies, there are like large heat sinks on top of the chip. How much those heat sinks suppress EM emission?
Yeah, of course that heat spreader basically removing the thermal problems, right? The temperature should be reduced, and that will give you the weight of extracting the heat powers from the die. But the metallic, this is a kind of the metal material, so in some sense that you can make the heat sink as a shielding, but you know that your emission happening not just the surface of the backside, but also from the sides and also on the board itself. So I would say that the heat sink would work, but this is just a part of it, part of the shielding mechanism. And one more thing I need to say that now people are discussing how that the thermal and EM things need to be solved concurrently. This is another answer.
Thank you for that interesting talk. I have two non-technical questions. The first one is related to the photo of the research group. Okay, looks like all the research group members are Japanese.
Yeah.
Okay.
You're
And actually, if you look at the research group in any university in the US or Europe, it will be a bit more diverse. So do you have a comment on this?
I agree with you. I agree. It used to be we have we also have some the students from China or from some other. Now, there is some difficulties nowadays. It's not so easy to allow to have the students from the outside, right? Because I'm working in the field of security. but one good thing is now that it's the start point for us to make international collaborations. It's happened really because of the security and the safety, as I mentioned, it's a kind of a mutual understanding based, right? That we want to ship our cars into Europe. We need to understand what's their nervous about their EM issues, kind of that. Always negotiations, or meetings, and the discussions are needed. That's the kind of the bilateral efforts people are really believing to have. In that aspect, we are always be involved in such international activities. Not just I can't get the students from the group, but our students are coming to that kind of meeting place to discuss. And of course, the students from the Europe, the students from probably from Egypt can join that meeting, and we can discuss at that time. So not in this photo, but we have good connections in the area.
Thank you very much.
Firstly, I would like to thank you for this talk and for the question. You have mentioned that we have some EM noise and we can just ignore them. So you showed us that we can suppress this noise outside from the chip. But nowadays we can design many chips on the same die. We can have them all together and we connect them with certain connections that are very short, so they are very near to each other. How can we suppress this much noise that are coming from the chips itself? Is there a way that we can suppress this kind of noise?
Okay, very good questions. But I think the noise problems has started same as the starting point of the design of the integrated circuits. We have a long history of the combating noise problems. There are many techniques like guard bonding and also the frequency changes, and also reducing some as I mentioned, that people are trying to make things packed to the clock edges. But another way is that you can disperse that the edges from the clock edges. You need to make things synchronous, but locally asynchronous. I think this is a topics that Ikeda-san is quite expert. And those kind of things are will be managed and already used for the managing noise. But what is the difficult problem now is it's not just a matter of the make things in a single chip, but nowadays we need to consider the separating the chips. Right? It's a heterogeneous integration, meaning that you can use the older techniques for the analog and the high-end techniques for the digital, and also the specific techniques for the memory. Now, how that we can put those kind of different chips in a single interpoler? Now, you need to consider what kind of noise mitigation techniques. So there are advancing technologies and the changing the supply chains change. You need to consider the new method, the new adoption of the noise reduction techniques.
All these methods are just for in the wave methods, or is there any methods that are electronic methods like some equalizers?
Oh yeah, in the circuit level, yes. It's as I mentioned that is a desensitization could happen in the design phase, right? That if you can expect to have your huge noise component at the specific frequency components, you can desensitize in the front end of your analog circuitry. For instance, you can put some chunks that will have your this type of the impedance chart, and that noise will be well absorbed in the time. Then the later chain can be decoupled from this particular noise at the front side, kind of that. So the prediction, if you have the good prediction of the noise, you can add some extra components on your circuit at some cost.
Thank you.
First, I would like to thank you so much for the very interesting presentation. I actually have like 10 questions. I'll just ask two. So the first question, in one of your slides, you mentioned that there was a design working at 106 megahertz, and the 20th harmonics were showing us noise at 2.1. My question is, do we have any information about the minimum clock frequency in digital design specifically that we have to be concerned about? Once we reach that point, then we have to do the EM analysis on our designs.
A good question. It's a kind of the system EM co-designing kind of that, right? That what clock frequency you can be tolerate, what's the lowest frequency you can tolerate for your system level performance. If you reduce the clock frequency, of course that you need to consider the higher number of the harmonics for the attacking the 2.1 gigahertz. The higher number meaning that the noise level should be well reduced. So in that sense, in that aspect, you can reduce the clock frequencies. But that wouldn't happen normally, right? Probably, I would say, is that you can use the kind of, how I say, it's a kind of the high frequency operation for the specific time zone. And then you can decouple your usage of the wireless from that highest activity digital time zones. Window is one of the way for the managing the interactions between the digital and the analog front.
Okay, and I have another question about actually the first couple slides when you talked about the fault injection on cars and the possibility of causing some accidents or anything due to the main function of the ECU. So, are you aware of any forensic analysis methods that can actually detect that kind of attack on cars?
Yeah, there is some way to sensing such kind of unexpected disturbance coming from the field. Yes, there are some sensors seeing that.
Thank you.
Okay, one last question.
Probably two questions.
Okay.
Sorry, Japanese. Please continue in Japanese.
Yeah.
No.
I want to ask if I want to go more in deep search, like in topics like this, for research knowledge or even for future work, considering that I'm or most of us is not that advanced in topics like this. What advice can you?
Oh yeah, I think that there are many good conferences. I think you can remotely attend or you can attend by yourself, right? It's, for instance, it's a conference between the IC chip design and electromagnetic compatibility and auto hardware security. Those three are combined together in some specific conferences. Like I will be organizing the one particular one. I would like to make an announcement here. It's EMC Compo. EMC Compo. This is the conference name. This is really dedicated to the EMC of the IC chips. And nowadays, hardware security people are also be joining. So I think this kind of interacting kind of the things you can learn from that conference, EMC Compo. Next year in Okayama, December, I'm chairing.
What's the question?
I think he is the last person. You can speak loud.
أقوم برسالة صلاح تبعتهم لصلاح مصطفى So I have a question about the Gleason route and the effect on electromagnetic compatibility and emission. So I'm working on something similar nowadays, so I've been into it a little bit. Simulations take a little bit of, not long time, simulations take a long time, so the feedback loop of doing a simulation, figuring out that the spin out doesn't work, I have to change a little bit of parameters.
Yeah.
Isn't there a way to have more like an estimate of of the leakage of the circuit rather than an actual number, more like an estimate that I can, so that the feedback loop is shorter, or maybe it can be make the feedback is quick?
Yeah, your question is about how that we can use the efficient use of the simulations, right?
Yeah.
Right? Yeah, of course. I think nowadays people are trying to pile up the simulation results for their further, after analysis by using the AI types of things, right?
Yeah.
That's one of the things that people, particularly in the area of EDA, they are working quite well. So I think you need to create many simulation results before.
No, that sounds like a good. Thank you.
Thank you.
Thank you very much.
Thank you. Thank you. Can I present certificates from our society and from
Hello everyone. First we'd like to thank our dear professors for joining us today. We're so happy to have you, and actually your lectures were very interesting, inspiring and insightful. Second thing, now on behalf of we are the SSCS Egypt section. We have our chair is Professor Samah Awasem, Samah Ibrahim Awasem, but he's not here today. I'm Dr. Mustafa, I'm Dr. Samah. I'm the vice chair of the SES chapter, and I have here Dr. Mustafa Hasmi, treasurer. Okay. Now we have this opportunity because actually every year we have an annual competition that we run for undergrad students related to the SSCS activities. So for this year we have we need to distribute the winners. For this year, we had 51 teams from 21 universities. They participated in the competition. And after running the competition, after the discussion, presentation, and everything, we have 3 winning teams. So we want to distribute this now. We have our, let's start with the bronze. With the bronze, okay. Actually, all the results, they are here now today to have their certificate. So we have the bronze award. This was for Helwan University. We have here we'd like to have the participants here with us on stage to distribute their certificates. We have Ahmed Abdelhamid, Mohammed Abdelhamid,
انا لسه ما اتحركتش لسه في تسليم شهادات
The second place, it goes to the Silver Award, and this was from Cairo University. Now we have the team Mohammed Asam, Bilal Ramadan, Murad Saad, and Hazem Mustafa. يا ريت شباب بس اللي ياخدوا السيرتيفيكتس يستلمونا لغايه يعني after بعد ما نوزع. Okay. The last one, which is the first place, which is the Gold Award, it was for Fayoum University. We have Adham Khalid, Bilal Suleiman, Mahmoud Ahmed, and Mustafa. Actually, they're not just certificates, there are financial prizes as well. Yes.
They have to come to me to get it.
Yes, that's why I told them please stay with us to have them. And this is to encourage you and all the rest to join us in next year, inshallah, the competition. They are good prizes. You can see them on the website and on our Facebook page. Thank you so much, and thank you, Professor.